Welcome. Today I'm going to talk to you guys about the next topic in our sequence here. If you recall, we started our first video talking about position, and then we moved on to our second video where we talked about how you recognize if something is moving or not. We called that motion. And now our third video is on looking at how we can measure how fast something is going when it is moving. So there's really two formulas, and these are the first two formulas that go with this particular concept. And the two formulas are split up into two different ideas, one of which is how fast you're going over a wide range of time, and the other is how fast you're going right now. So you can see that there are different ideas, and so we're going to have to take them separately to make sure we understand what's going on with them. For that purpose, I'm going to go ahead and split this video into two parts so it breaks it down a little bit easier for you and makes it a little bit more digestible, I think. So that's my hope for you guys, is that makes sense. So again, this is 009 on speed, but technically this is 009A because we're going to do two parts to this. So our first part is really how fast you're going over a wide range of times. This is the one that you're probably most familiar with. This is the formula that you learned in middle school, and so it should be a pretty decent review for you, I hope. But it is based off of our ideas of motion, and so we put a little bit of a physics spin onto it. Okay, so here's our first topic here, and that is, how do I know how fast something moves? Well, you guys have you saw in the last video how we know if something is moving, and so I'm going to go ahead and draw that out just so you get a sense again. So here's a horizontal surface, as horizontal as I can make it using my system here. And on top of that horizontal surface, I'm going to roll a ball. Why a ball? Because a ball is much, much easier to draw than the car I was drawing last time. So when you first notice it, you notice that it's at this position right here. So we're going to call that x sub 1. That's where you notice it. Later on, you may notice it that it is right here. And that the fact that it has moved from x1 to this new x2 gives you a pretty good indication that it obviously is moving, right? Now, it doesn't make a lot of sense to have an object move and not take any time for it to move. It would be a wonderful world if we lived in a Star Trek-like universe where we had technology that would teleport us from one place to another without there being any intervening time. But unfortunately, that doesn't happen. So if we were going to go ahead and analyze this motion, we would really need to look at two things. The first thing is how far it moved. In the last video, I called that delta x. That's the change in position. I want to tell you right now that delta x has a special name, and it's something that I'm going to use a lot, and I'm not even going to think about it, so I want to make sure you've got it down. Delta x is actually called displacement. Displacement just means, well, you can look at the two different parts of the word, right? Placement means where it's located, and dis, in this case, means it's changed from that position. So displacement is our new term for delta x. There we go. So there it is, displacement. So I'm going to say that often, and you're just going to have to know what that is because I'm not going to think about it. And that's how it's really referred to, displacement, as this delta x right there. Okay, the other thing that we have to take into account is the fact that this displacement had to happen between two different periods of time, or two different instants in time. So when you first noticed the ball, let's say that was time t sub 1, and then later on when you noticed it again, that was time t sub 2. And so what we're really interested in is the difference in the times, how long it took to go from t sub 1 to t sub 2. What's the difference in those times? And just like we had change in position here is displacement, we can also have the change in the time. And so now we have a basis for us to go ahead and describe this. Now, a college physicist might actually write a subscript on each of these, where you might have delta x 1, 2 and delta t 1, 2, so that you know for a fact that it's going from this first time measurement to the second time measurement, or the first position measurement to the second position measurement. I'm not going to do that because it might get confusing for you. And really what I'm trying to do is to develop the actual formula for you. In middle school, you may have remembered, or you may remember, that you probably learned something that said the rate of an object is equal to the distance that it travels in a certain period of time. You guys do this all the time, right? If I were to say, how fast did you go when you went from your house to your friend's house, and your friend lived 10 miles away and it took you an hour, you could say, well, distance was 10, time was at 1 hour, so my rate was 10 miles per hour. Maybe you're on your bike. So that's the formula that you learned in middle school. Well, guess what? This formula that we're learning today, it's exactly the same thing. We're just going to use fancier terminology to go with it. This formula is our first formula in physics, and it has the number 2.1 on your formula sheet, and it looks like this. The average speed, that's a V right there, which is actually for velocity, which we're going to transition to later on. But for right now, let's just call it speed. There is a difference, if you can believe this. There's a difference between speed and velocity in physics. Everything has to have its precise definition. So the average speed is equal to, just like here we had the distance, obviously here we're going to talk about not distance, but its displacement, delta x. And then here we had the time, so it makes sense to use our delta t right there. And so here's our first formula for physics. It's the definition of average speed. There it is. If you wanted to write it out a little bit more thoroughly, you could separate this out. Remember, the delta just is something that I do because, and all physicists do because we're lazy. You could be more precise if you wanted to and say, on the top of the formula, it's x sub 2 minus x sub 1. And on the bottom of the formula, it's t sub 2 minus t sub 1. Again, we're trying to find the differences between those two. Either way, this is all the same formula right there. So this formula and that formula that you learned before are the same thing. So again, this is not anything new. It's just a review, but then we put the physics spin on it by using our more precise terminology. Now, it's important that we use that precise terminology because later on we're going to build off of that. So we want to make sure you got that down pretty well. Again, that's our 2.1 formula. So let's take a look just for a second here at the next slide here, which is asking us again, how do you talk about that mathematically? Well, I just gave you the formula, so I'm going to go ahead and write that again, just so we can refer back to it for a second here. Again, that formula was 2.1 on our formula sheet, and the speed, it's the average speed, is equal to change in position, or the displacement, divided by the change in time. There we go. One other bit of information that you might come across, old school people and more mathematically minded people will write average speed with an overbar above it. That overbar means average. I try not to do that as much as I can, so because I think it's confusing at this level. But at the college level, you may see that, so don't freak out by it. Just a side note, if you're in calculus, you're going to see this formula, exactly this formula again, when you see something that looks like this. One of the first derivatives that you learn is that the speed of an object is equal to dx dt. This and that are equivalent, so you don't need to worry too much about that. If you're not in calculus, don't worry about it, just ignore it. Pretend like that little part of the window doesn't even exist. It's totally fine. Okay, so again, it's the average change in position over the average change in time. Now, check this out just for a second. Does it tell you anything about how fast you're going at any particular time? The answer is no. So let's say here's your house. That's your house. And here's your friend's house. And the difference between these two is, what did I say, 10 miles before? Let's use kilometers because I want to try to keep it metric here. 10 kilometers. So we use 10 kilometers, and then it takes us, let's say, I don't know, 1,000 seconds to get there. So the time is going to be, so we start off here with 0 time, so t sub 1 here equals 0, and then t sub 2 here equals 1,000 seconds. And because this is physics and we use the MKS system, we have to remember that we can't use the distance in kilometers. So we could, but we're not going to. So we're going to use it in meters. So there's 1,000 meters in a kilometer. So to convert that, I'm just going to make it 10,000 meters. So what's your speed there? Well, your speed measurement is, of course, an average speed. There we go. Is equal to the change in displacement, or change in position there, your displacement, 10,000. And that's in meters, divided by 1,000 seconds. And so you can see that the answer to this, of course, is going to be 10. And the units then, you still have meters on the top of the fraction, and you still have seconds on the bottom of the fraction. So the units are meters per second. This is important because all units for speed in physics are going to be in meters per second in our class. We need to have that in meters per second because if you're not, then you're not using this MKS system, and the other units that are based off of meters and kilograms and seconds won't work. So you have to do more conversions, and really nobody wants to do that. Okay, now does that tell you anything about how fast you're going at any particular time? Very quickly, no, it does not. So look what your speed actually could be. At any particular time, you could have started off from home, accelerated, gotten faster, cruised along at a certain speed, hit a stop sign and stopped, and then started up again, accelerated, and then cruised along at a certain speed, and then hit a stop sign and stopped, and then come back up, and then finished off your trip by arriving at your friend's house like so. So this 10 meters per second doesn't tell you anything about what's going on during the actual time. It just tells you a broad idea. And so that's why it's an average velocity or average speed. Okay, hopefully that makes sense to you. So I'm going to go ahead and wrap it up there for this first section. This is, again, 009A. 009B is going to be about how we use the average speed to figure out certain things about how you're going, how fast you're going at any one particular time, which is actually deceptively tricky. Please don't forget to do your note sheet for this, and then your interesting question form. You can do the same note sheet and interesting question form for both Part A and Part B if you want to. That would be better for me, at least. Hopefully for you as well. Okay. With that, I'm going to tell you thanks for watching. Hopefully it made sense. Hopefully, again, we're easing you in gently. The next formula we're going to learn in 009B is something you've probably not seen before in this way, so you want to make sure that you're ready for it. So make sure you've got a good foundation before you continue on. Thanks for watching. Have a great day.